Hi everyone. So we're gonna like end the poster session and continue with Niao's talk. So Niao is an assistant professor in the Department of Industrial and Enterprise System Engineering and Coordinated Science Laboratory at the University of Illinois. And today she's going to talk about smooth game in machine learning beyond GANs.
All right, thank you for the introduction, and I would also like to send my thanks to the organizers for such a wonderful workshop, and it's indeed a great pleasure to be here and present some of our recent work. So, what's going on here? Okay. So I'm sure you're going to hear lots of talks on GAMs during this workshop, and so I'm going to talk about something slightly different. So in particular, I'm going to kind of show you that indeed there are lots of GAN-like problems and smooth game applications in machine learning, and hopefully our understanding of GANs can be leveraged to advance many of those applications and domains as well. Okay, so to start with, I believe we have seen enough evidence how optimization plays a central role in lots of machine learning applications, ranging from deep learning to generative models, all the way to reinforcement learning. And we have seen tremendous algorithmic developments centered at solving empirical risk minimization in the past decades. But in fact, games are also everywhere in these applications, not just in GAMs, but also in many others. And I will give you some interesting examples in this talk. And in particular, I'm going to focus mainly on these zero-sum two-player games, and which essentially equivalent to solving minimax optimization problems. Okay, so here's a brief outline of the talk. I will first show you that how minimax optimization frameworks can be used as a powerful technique and a powerful framework to address many other machine learning applications, and then we will see what are the available tools to solve them both in the convex and non-convex regimes. Okay. So let's look at examples first. So the first example I'd like to discuss is related to reinforcement learning, and we all know that this is kind of driving force behind many of the recent breakthroughs in artificial intelligence, ranging from defeating the world champion in games and designing self-driving cars and also training robotics. And in a reinforcement learning setting, an agent tries to select actions at each round in order to maximize the long-term reward. So the Markov decision processes has been widely used to describe the environment of a reinforcement learning, which contains 4 components: the state and action state spaces, and the probability transition matrix, which is often unknown in the RL setting, and also the reward functions, which are observed at each round of the game. And the goal here is we want to try to find out what is the optimal policy in order to maximize the long-term reward. Okay? So it is known that there are 2 fundamental tasks essentially in reinforcement learning. One is to do policy evaluation, saying that if we're given a policy, how can we evaluate how good each state is? And this is usually referred to as a value function. And another fundamental task in reinforcement learning is essentially to do policy optimization. How can we find out what is optimal policy, or what is the best strategy in order to maximize the long-term reward? And both of those problems can be characterized into the language of Bellman equations. And as long as we know how to solve those Bellman equations, we can find out what are the value functions and also what are the best policies. And indeed, a lot of the classical algorithms in reinforcement learning, such as temporal difference, Q-learning algorithms, they're essentially based on solving those Bellman equations through stochastic dynamic programming. So recently, there has been also a growing interest in trying to integrate Bellman equations into the framework of minimax optimization in the hope that we can design provably efficient algorithms or primal dual algorithms or actor-critic algorithms to solve reinforcement learning. And this is particularly important, especially in the case when we use function approximation, because we know even for the popular algorithms such as Q-learning, if we apply function approximation, they might not be guaranteed to converge, okay? Actually, sometimes in reality, they will fail to converge. So there has been actually an interesting line of work towards trying to solve those through an optimization perspective. And here I have listed a couple of references, both for policy evaluation and for policy optimization. And particularly, I'm going to discuss one of our very recent work, which tries to address policy optimization with nonlinear function approximation. Okay? So to start with, here is our our goal here. We want to find out what is optimal value function by solving this Bellman optimality equation. Okay? And this is known to be kind of challenging, mostly because of this max operator, which is extremely non-smooth and could cause some instability in training those algorithms. So our first step is we try to smooth out this operator, max operator, by replacing it by the log sum exponential operator. And this smoothed value function will then lead to the equivalent smoothed Bellman optimality equation. And here we would essentially want to solve this smoothed Bellman optimality equation, which is kind of in this simple, nice form here. And a natural way to solve this is through just by, like a standard approach is solve it by minimizing the mean squared Bellman error here. And here, this is also a simple minimization problem. It's not necessarily simple, but it looks like a simple optimization problem where we try to minimize over the value function as well as the policy pi. And we try to, and as you may see that this objective here has this nested expectation inside of those square loss function, which usually causes this double sampling issue in which says that we need to have at least 2 observations in order to get an unbiased estimator of the gradient, which in practice, oftentimes we can only observe 1 state after each action choice. Hence, in order to address this issue, we propose a unique dual formulation to this minimization problem by introducing a dual player mu into the game here. And as you can see that this can be viewed as a zero-sum 2-player game, so where the primal players here essentially represents the value function and the policy here, and they're trying to kind of minimize the smooth Bellman equation gap here. And the dual player mu here, which is now a function, tries to kind of enlarge this discrepancy by reweighting these equations, okay? And this minimax optimization framework actually comes with several main advantages. First of all, as we can see that here, we no longer to deal with this conditional expectation anymore, but instead we only deal with this joint distribution, which means we can easily kind of estimate the objectives through basically of policy samples that we observe in practice. Secondly, based on that, we can basically apply a lot of the existing kind of favorite stochastic gradient descent-based algorithms to solve this type of minimax optimization framework. And an interesting highlight here is that I think this type of minimax optimization framework actually serves as a very unified scheme in order to kind of incorporate to address problems both with or without functional approximation. Also, since it comes from an optimization perspective, it also allows us to design more kind of principled algorithms, like actor critique algorithms, to solve those reinforcement learning problems. And I would also like to highlight that actually, with our minimax optimization framework, we've shown that actually in practice, it performs very well comparing to the current standard of the state of the art. And another important thing I would like to emphasize here is that this type of framework also helps us to kind of extend it to many other settings, like if we have constraints for the policies, or if we want to deal with distributed settings, and those can be directly extensible, okay? And the only caveat I would like to point out here is that depending on what type of nonlinear functional approximation we introduce into the minimax optimization framework, we may essentially end up solving a non-convex, non-concave saddle point problem, and we may suffer from some of the training instability as we see in many of the GAN problems, okay? Yes?
I have a question, just given the talk by Joëlle Pinault on reproducibility in NRL, she showed a lot of these pretty plots. And she said they varied a lot with random seed and everything.
Right.
So here, how many seed did you use, or?
So that's a very good question. As you can see that here, we also compute those average rounds, like the performances. So we take into account of different randomcies. And the number of randomcies we use here is like about 5 or 10, yeah. Not a lot, but yeah.
Yeah, that's too low.
Yeah.
See your talk.
Yeah, but I would say the kind of main message here is really this type of frameworks helps, at least for those simple modular tasks, okay? And we're looking forward to see those can be implemented in real applications as well. Okay, so the second example I would like to discuss is related to estimating exponential family distributions. And exponential families are, I think, without any doubt, is the most elegant and simplest class of distributions that covers a lot of our commonly known distributions such as Gaussian, Poisson, and many other distributions. And here I'm focusing on this generalized version of exponential family, where this natural parameter f is now represented by a function that comes from some function space such as a reproducing kernel Hilbert space. And hence this log partition function af, which is in the form of this, can be viewed as a convex functional here. And this type of exponential families are actually widely used in a lot of machine learning and statistical applications, such as hypothesis testing or even like learning graphical models. And the central goal in those problems are trying to estimate those parameters of the exponential family. And the standard approach is, of course, through maximum log likelihood estimation. And in this case, the MLE essentially reduces to solving the following maximization problem. And this maximization problem, although it looks kind of simple, it suffers from several kind of disadvantages. First of all, this problem is well known to be ill-posed in the infinite dimensional setting. Therefore, a common remedy for that is to try to add some regularization terms to it in order to get a existence of solution. Secondly, the existence of this log partition function makes solving this problem extremely difficult because this log partition function involves a huge integration inside and it can be computationally intractable. So existing approaches such as score matching tries to avoid computing those log partition function, but instead considering some other objective based on minimizing feature divergence, okay? Or there are also other algorithms such as contrastive divergence tries to kind of estimate the gradient of those partition functions based on a sequential MCMC sampling steps. And both of those existing methods can be extremely computationally expensive with large data sets. So here we try to propose a new kind of minimax optimization framework in order to handle those difficulties for large data sets. So to start with, we've shown that in particular, this log partition function actually enjoys a very nice simple dual representation, and we can simply translate this maximization problem into a maximum problem by introducing those dual variables, which are now distributions Q, and we have those central dual representation given by the KO divergence here. And by strong duality, this can also translate it into a min-max problem in the following form. And with a close inspection, you can see that this actually resembles a lot to the many of the GAM formulations, such as the Wasserstein GAMs or the MMD GAMs, with only except with two notable differences here. So this again is a like zero-sum two-player game. Here, our primal player is our model f that we try to learn for the exponential distribution, whereas our dual player here is the underlying distribution. And as you can see that unlike other GAN formulations here, our dual player or our model here, which can be viewed as sort of as a discriminator, does not necessarily need to belong to like the Lipschitz continuous function. Here we assume it naturally comes from some, say, reproducing kernel Hilbert space. Secondly, naturally, in our objective, we have those regularization terms from the entropy or from the regularization for the model itself, and which makes those problems actually, in fact, strongly convex and strongly concave in nature, okay? So despite of that advantages, like dealing with those KL divergence can still be challenging because it requires explicit formulations or representations of the density function Q. Hence, we kind of apply a second layer of dual representation by introducing a third player mu into the game. And this role of this third player is really trying to just to balance out the distribution P, Q, and the prior P0, okay? And this minimax optimization framework, again, has several outstanding advantages. As we can see that this objective here are only like a bunch of expectations, and we can kind of assess those objectives or their gradient through just samples from the data we have or from the samples from those distributions Q, okay? And secondly, as you can see that there's no log partition function at all in our objective, hence we don't need to actually compute log partition functions, we don't need to do any MCMC samplings, and solving this problem can become very efficient if we use those traditional stochastic gradient descent type of algorithms, okay? And those are some of the highlights I just mentioned. And in fact, when we apply this type of strategy into some real, like some simulated data, we see that the exponential family that we learned from this minimax optimization framework actually fits very well to the data, okay? And again, as I said, there might be some caveat, although this problem from the very beginning is a convex concave problem, but once we introduce some sort of parameterization into those functional approximations, we might end up solving some non-convex optimization problems in the end. And we have a poster at another workshop, and if you have time, like in the afternoon, you are welcome to visit our poster there. So if you're not convinced yet, I'm going to give you another example that shows how minimax optimization framework can be used as a powerful framework to address some of the computational challenges in another classical machine learning application called approximate Bayesian computation. So approximate Bayesian computation is also known as likelihood Bayesian inference, which is commonly used in like large-scale dynamic systems where we don't really have a closed form likelihood, but we know how to simulate it. And this also has close ties to GAN as well, or generative models or implicit models. So a classical algorithm for solving approximate Bayesian computation is mainly based on some rejection-based methods. So for instance, so most of those algorithms, what they do is follow some trial and error scheme that tries to accept only parameters that gives you or produces simulated data that's similar to the observed data. And the similarity measure is essentially characterized either through sufficient statistics or distances between the empirical distributions, okay? And those methods are also well known to suffer from several kind of pitfalls. One of the main kind of pitfall of those algorithms is that they suffer from various or multiple level of bias, either coming from having only insufficient statistics or having to kind of estimate the distances between distributions, or from like only using non-zero tolerance levels for the acceptance rejection criterions. And also those methods can also have very low acceptance rate in practice, especially for high dimensional problems. Therefore, there comes the rejection-based ABC algorithms, which essentially tries to fit just a regression model between the simulated data and the parameters. And then they try to solve this regression model based on all kinds of kernel methods or distribution regression methods. Those are kind of the state of art in this area. And as one can see that none of those methods actually scales up for large problems due to the use of kernel matrices. So here again, we try to kind of revisit this problem from a minimax optimization perspective. So here we simply propose that we can just estimate the posterior by matching the joint distributions. So, and this ends up with this simple objective where we try to minimize the F divergence between the joint distribution represented by the likelihood and the prior, as well as the joint distribution represented by the posterior and the marginal distribution. And this problem, while it looks kind of simple, actually it is not readily solvable, as we don't really know what is the likelihood function. We only know how to sample from it. So here again, in order to deal with those problems, we're going to again apply our magic wand here. As you probably can tell, we're going to still use this differential dual representation, and this will lead us to solving the following optimization problem, which again is a zero-sum two-player game where our primal player is this posterior distribution that we're trying to learn. And the dual player here can be served as some discriminator that distinguishes between the joint samples we have and the joint samples from the posterior, okay? And similarly, as you can see that assessing the objective of those minimax cost functions is kind of simple, because as long as we have samples, we can estimate the gradients and we can use the cast gradient type of methods to solve it. And again, similarly, like the GAN problems and the problems I mentioned before, this might end up solving some non-convex, non-concave saddle point problem, okay? And beyond these applications I just mentioned, there are also tons of other examples in machine learning which use these minimax optimization frameworks, and which I'm not going into too much detail here. But the punchline here is really that minimax optimization or saddle point technique can be used as a powerful scheme to address many of the computational and theoretical challenges in other machine learning applications. And the interesting question here is really how can we solve them in a principled manner, right? So here comes to my second part of the talk. So first of all, I'm going to show you that actually how to solve minimax optimization problem has been well answered and well established in the convex concave regime. And we're going to kind of use some of those ideas here to see how we can extend to the non-convex case, okay? Any questions so far? Okay. So normally a solution to a minimax optimization problem, as we all know, is referred to as a saddle point, and those problems are also called saddle point problems. And for convex concave cases, we focus on problems where phi is convex in one variable and is concave in another variables, and this appears in many applications. Also applies to some of the applications I mentioned earlier if you're doing the parameterization carefully, okay? And indeed, solving convex concave saddle point problem shares a lot of similarity as solving convex minimization problems. Both of their solutions can be characterized by first order methods. Both of the solutions can be characterized by first order optimality conditions. Both of them can be solved by a lot of first order methods, and both of them have kind of nice criterions for characterizing the accuracy of the solutions, okay? And more importantly, as many of the other speakers have mentioned, that both of them can be characterized in a unified framework called variational inequality. So mathematically speaking, what is variational inequality trying to do is, say for instance, if we're given a domain X, we're given some operator F, we want to try to find some solution X star such that any feasible direction from X star in this domain X has an acute angle between the operator at X star, okay? And this essentially is the optimality condition for a lot of minimization, convex concave saddle point problems, and even convex Nash equilibrium problems if we set the operator F to be the corresponding gradients. And it's also worth to mention that for all of those problems, the operator F is monotone operator. And some of the other speakers also point out this associated variational inequality, which is called the Minty variational inequality. And so from basic theory, we know that if a solution, or if the operator is pseudo-monotone, which satisfies this condition here, it implies that a solution to the variational inequality, which is often termed as strong solution, is also going to be a solution to the associated Minty variational inequality, which is usually termed as a weak solution, okay? And in the opposite direction, if the operator F is continuous, then a weak solution is always going to be a strong solution. So in the minimax problem, actually the Minty variational inequality serves as a sufficient and necessary condition to characterize the saddle point, whereas variational inequality only serves as a necessary condition for saddle point. And indeed, solving variation inequality with monotone operator has nearly 50 years of history in optimization society. And this actually starts from the very simplest algorithm called the projection method in 1970, which is sort of as a projected gradient descent, as you can see here. And it's well known from like 1970 that indeed you need to pose some strong monotonicity assumptions in order for the algorithm to converge. Okay? If you don't have strong monotonicity, you only have monotonicity, then this algorithm will not converge even if you take average, unless you use decaying step sizes. Okay? Therefore, extra gradient method was proposed later, and basically, the algorithm tries to perform 2 steps of gradient at each iteration, and it is known that it does not require strong monotonicity in order to guarantee convergence. Just pseudo-monotonicity is sufficient enough. Okay? And also, there is proximal point algorithm, which was also proposed in the 1970s, that tries to iteratively solve a subproblem of variational inequality with strong monotone operators. And this algorithm is also known to converge linearly if the monotone operator is strongly monotone. And it worth to pointing out that all of those algorithms can be viewed as fixed point iteration algorithms. And especially if we look at extra gradient methods, this is also essentially a fixed point algorithm as well. And there are also lots of other hybrid methods which tries to solve those subproblems iteratively through other subroutines, and I'm not going to discuss too much of details there. But let me just kind of recap a little bit of what is extra gradient method, as many of the other speakers have pointed out. So here I'm going to discuss the so-called mirror-prox algorithm, which is essentially a generalization of extra gradient method by exploiting some of the underlying non-Euclidean geometries. This is especially important when your domains has, say, it's like a simplex form or other kind of convex compact domains. You might want to use nonlinear or non-Euclidean divergences here for the projections. So basically what this algorithm does is at each iteration, it performs 2 mirror max, both at the same prox centers, xt, but with the operator f evaluated at 2 different points, one at xt, one at yt, which is the intermediate solution yt here. And it was established from by Nemirovsky in 2004 that as long as your f function is monotone and satisfies this condition here, this can also be generalized to the Holder continuity as well. So if L is 0, then this means the operator has to be bounded. If M is equal to 0, this implies that the operator has to be Lipschitz. Okay? And the inaccuracy to the variational inequalities can be bounded by this kind of standard term. And this essentially implies that the algorithm achieves an ergodic convergence rate in the rate of 1/t for monotone operators that are Lipschitz, and for monotone operators that are bounded, it achieves a 1/t, but you have to use decaying step sizes. Okay? And all of those results kind of extends or can be translated into the convergence of minimization problem or minimax optimization problems directly, okay? And of course, there are tons of other variations and hybrid combinations of algorithms for solving variational inequalities with more complicated structures, such as mixed variational inequality or stochastic variational inequalities, okay? And all of those algorithms can be customized to solve minimax optimization problem, essentially, because those are designed for a more general class of functions, okay, or problems. And beyond that, there are also tons of other algorithms that are designed particularly or pertained to the minimax structure or even bilinear structure. And an important family of algorithms is the Chambon-Epoch primordial algorithms. And there are lots of follow-up works for primordial algorithms for these bilinear structured problems or even for general convex concave saddle point problems. And I guess my point here is really that there are tons of work. There are rich optimization theory towards like convex concave saddle point problems, and I think if you're happen to encountering some problems with convex concave structure, it's always worthwhile to check into those literature rather than kind of reinventing the wheels, I guess. So what about non-convex case? Since I only got 5 minutes, so I will quickly go through some of the positive results we got on this setting here. So again, for non-convex, non-concave problems, as I mentioned earlier, there exist lots of applications, not just GAMS, but many others, okay? In this case, first order stationary point is not necessarily always going to be a saddle point, okay, unless we pose some strict assumptions. So for instance, one of such assumptions is that suppose your problem is variational coherent. So this is kind of also a concept that straightforwardly generalizes a notion of coherence for the non-convex minimization case. Suppose any saddle point of your minimax optimization problem satisfies the min-t variational equality, with equality holding true if and only if at a saddle point. Then you can show that indeed all of the previously mentioned algorithms such as projection method, proximal point algorithms, mirror prox algorithms will converge as long as you kind of set a proper step sizes, then they will converge. But of course, such type of assumptions can be too strong and unrealistic for many applications. Therefore, it's more reasonable and realistic to say just to hope for just first order stationary convergence for general non-convex, non-concave problems. And this essentially means that we want to find a solution to a variational inequality, but without pseudo or monotonicity in those cases. And the immediate questions we want to ask is, does the previously mentioned algorithms designed for variational equality still converge in the non-convex, non-monotone setting? And under what conditions do they converge, and how fast do they converge? So to address those questions, we also looked at a very special class of problems called weakly or relatively weakly monotone operators. So here, this notion also generalizes the so-called weakly convexity that was popularly used in analyzing stationary convergence for non-convex minimization problems. And the idea here is that suppose you have an operator F, which is not necessarily monotone, but if you add a strongly monotone operator to it, it becomes monotone, okay? And as I mentioned earlier, that all of the proximal point algorithm or the mirror prox algorithm can all be viewed as sort of a fixed point iteration algorithms. Therefore, a standard or a natural measure for stationarity gap is through those differences before or after taking the operator, okay? And here some positive results we got is that, okay, indeed, if you assume that your variational inequality is weakly monotone or relatively weakly monotone, you can show that in fact mirror prox algorithm and the Bregman proximal point algorithm both enjoy some nice 1/t stationary convergence. But one caveat here is that all of those convergence does not necessarily imply that your solution itself converges to a saddle point, okay, or a first order stationary point. And those rate does not also transfer to the convergence of those solution itself as well. And I'm glad to see that actually there are lots of recent works that tries to kind of give a more theoretical understanding on solving non-convex and non-concave problems, but as you can see that many of those works actually has either only asymptotic convergence guarantees or they are relies on some strong assumptions, and many of them does not cannot really tell you what is actually the optimal sample complexity or what is optimal iteration complexity you can get. And I would say there are still lots of things and lots of open problems that remains to be addressed in this direction. And just to quickly wrap up, I hope I've convinced you that there are various GAN-like problems and smooth games applications in machine learning that needs to be addressed. And if you're a GAN expert and if you're looking for something interesting, this might be some nice options. And also there are rich existing library for solving convex concave problems. And it's worthwhile to check those literatures as well if you're really solving a convex concave problem. And the last but most importantly, there are much work needs to be done, and I'm looking forward to see more efforts towards those directions. And thank you. And I would also like to kind of acknowledge my collaborators on those work, and thank you for your attention.
Thank you for the talk. Any question? Yes, Simon?
Yeah, so very nice talk. I'm glad you were able to show all these different examples. But in all these examples, you use often like this strong duality, functional duality. So as soon as you start to put non-convex parameterization, what do you get there, and what's the interpretation? Like, for example, like let's say we just do the maximum likelihood estimation. Like
So when we use the central dual or strong duality, we're only looking at like the original problem, which is convex, before we introduce any parameterization, right? Once we introduce parameterization, that's like for the minimax problem. And of course, global convergence is at stake. Although the original problem is convex, right? But we end up solving some non-convex, non-concave problems, meaning that we're not always guaranteed to get a global saddle point or a global solution to the original problem.
But let's say we look at this example, right?
Sure,
so
yeah.
At the bottom. So now if you have that the F space is non-convex, what's the interpretation of this problem? Like, is this still a maximum likelihood? Is there still an interpretation as a penalized maximum likelihood, or now it's just a whole different criterion?
So first of all, for this particular application, we're looking at the case where F comes from some reproducing kernel Hilbert space. So here F still remains reproducing kernel Hilbert space. Okay, so we're not changing that part. But this Q comes from when we introduce the dual variables. And that part is kind of flexible depending on how we want to parameterize it. So if we kind of restrict this to a smaller set or a special kind of parameterization schemes, that essentially breaks from here to here, right? So it sort of can be viewed as you're adding essentially some regularization to the original problem, because you're dealing with a constraint dual problem here. So it sort of can be viewed as a regularized problem to the original one. So the solution to this after parameterization, unless your parameterization is flexible enough, it will not going to be exactly the original problem. Yeah, but that's a very good point.
Any other question? Okay, I have one. Like you've mentioned lots of convergence rate in this talk, but like most of the time for like the batch setting, and what happens in the stochastic setting?
I think that's a very open problem right now. And one thing that we can do is, as also some of the other speakers has mentioned, is that you can sort of view the problem as a batch setting, but when you kind of solve the sub-problems, say like the projection step or the solving the auxiliary variational inequality through proximal point operators, you can solve those sub-problems iteratively through some stochastic algorithms. That will help you, that will at least guarantee some convergence. But if you start with the very beginning with some stochastic mirror-prox algorithm or stochastic proximal point algorithms, for the convergence right now, I think is still open.
Thank you. So if there is no any more question, let's thank the speaker again. Okay, so now we're gonna continue with two contributed talks. And the first talk is gonna be given by Volkan. And it's gonna be about mixed Nash equilibrium in GANs.
All right. How was everybody? All right, so I'm going to try to inject a little bit of poison into the discussion so far. People really like to focus on the existing definitions of GANs, we're going to try to twist it and try to apply some algorithms that have additional properties. So I think I'm preaching to the choir here when I talk about the importance of learning distributions. And it turns out to be a very interesting, very compelling balancing act between data, models, and computation. Now, if you can actually figure out how to characterize distributions, there are several upshots like data generation, compression, many interesting image generation. And the current trends go from, simple LDA models towards more complicated models that, generate literally hotel room pictures, right? And of course, with more power comes more challenges, so to say. The problems are becoming more and more difficult, as well as, non-convexity is out there. Now, part of this workshop, we're going to highlight the generative adversarial networks, which I think has thousands of citations now. The idea there is to have this nice, let's say, minimax game between a generator neural net, which tries to generate some fake data, and a discriminator neural net that tries to authenticate this based on what the real data says. And there are several variants exist. I'm not going to cover it all, but the one that I'm going to focus on is the Wasserstein-GAN. And if you look at the Wasserstein-GAN, it's again naturally cast in this minimax optimization form. And I mean, previous speakers also talked about this. So here, just to set up the notation, theta is the parameters of the generator neural network. W will be the parameters of the discriminator neural network. And this is a difficult non-convex problem. Even though there are several algorithms that claim success, it still remains strong in terms of challenging people. Right? Now, the theoretical challenges to this is that the saddle point might not exist. If you look at the original GAN formulation, it's well defined. But the moment you start restricting your generator to a neural net and the discriminator to a neural net, like Simon asked just a couple of minutes ago, all of a sudden you get into situations where the saddle point might not even exist. And to my knowledge, there's no provable algorithm for this particular beast. Right? Now, of course, things like theoretical challenges have never been has never been a barrier for people applying existing algorithms and demonstrate empirical success. And of course, whenever you have a problem like this, you try out the simplest algorithm, stochastic gradient descent. It does not work well in practice unless you do heavy graduate student descent on the parameters of it, the learning size of it, step size for it, And then, of course, we rely on the faster methods like ADAM, RMS prop. There are other variants, Yogi, and I can't really catch up with the literature currently. But these methods turn out to be a bit unstable and again require graduate student descent. So hence we have a workshop on this, right? Now, what I want to do is exactly inject the poison here. So here's the objective of the Wasserstein-GAN. And I'm going to view this with some insights from game theory as a pure Nash equilibrium game. Right? Here, in this case, you basically fix a strategy for your generator and you're done. Right? And if you think about playing rock, paper, scissors, sometimes mixed strategies are a bit more appropriate in terms of understanding the fundamentals of the problem itself. So what we're going to propose a new objective, which is arguably a harder objective to optimize. And the idea here is that as opposed to learning a single generator and a single discriminator, why don't we try to learn distributions over generators and distributions over discriminators? Yes, Jason?
Can you talk about more why it doesn't exist?
So the question is why would the saddle point not exist, right? So, I mean, if you think about it, the discriminator plays the role of a dual variable, and you're restricting, for example, the dual variable to belong to some function class, right? In the end, if you write this as a minimax problem, the max player may not completely optimize to give you correct gradients for the min player. And there are cases where you might be able to construct that it does not exist, because in general it does not. If you write general, you know.
If W is compact, the max problem has, it's a function.
Sure.
So then if theta is compact, then, there is a, the problem, the problem is solvable. It's not min-max is not necessarily max-min, but
Sure.
this problem is there is a well-defined solution.
Sure, sure. Fine, but again, the nice saddle point may not exist. I mean, you are the expert on this, but
Is it doesn't exist or we can't find it?
oh, so that I don't know, right? That's why I say might not. That's why I'm saying that might not exist, right? Right. I did not say that it does not exist. I said might not exist. Right. All right. So in this particular case, what I've just changed is the problem became from learning generator and discriminator parameters to learning distributions over the generator and discriminator parameters. So arguably much more difficult. But in terms of writing down the optimization formulation, it becomes much nicer. Because for this particular case, the existence of the Nash equilibrium is guaranteed. Okay. Now, we can also look at the same problem. The notation also becomes a bit easier. In fact, it becomes a convex, nice, bi-affine matrix game. The caveat here is that because we are now trying to learn distributions over the generated parameters is in infinite dimensions. Right? Now, the way you get to this is actually simple. It uses something called the Riesz representation. And there's like a nice one-to-one correspondence between the terms here to the terms here. Okay. Then the moment you see this nice minimax game, what you can do is just think about the algorithms that exist, but in infinite dimensions. Things like, let's say, the entropic mirror descent method, right, by Beck and Tibble. So if you just define the entropy function and just put additional technical assumptions, you can define this infinite dimensional mirror descent method that uses this mirror map to go back and forth with the entropic mirror map. And you can actually generalize these discrete algorithms to continuous spaces. And there's, of course, the mirror prox version of Arcady, which is also possible here. Now, when you do this, you can actually write down very simple algorithms that are like very innocuous looking. So the entropic mirror descent has this form, and the infinite dimensional entropic mirror prox has the extra gradient form. What you can do is under the setting, you can easily show that if you use the deterministic gradients, you have the simple convergence rates with square root of t for the entropic mirror descent, and of course for the mirror prox in the average 1 over t, which were also given. But if you only use the stochastic derivatives, then the rates suffer. They both have the square root of t kind of convergence rate. Yeah? These are for the bi-affine game that I defined directly. Yeah. Yeah. Now, the elephant in the room at this point is these are nice, but how do we run it, right? So I just showed you maybe a nice way of formulating the problem, but if you actually want to implement this, how do you do this is the really important question. Now, what you do is, if you just look at the entropic mirror descent, and you kind of unroll the iterations, you can see that the updates on the iterations has this nice exponential form with a normalizing constant, right? The same thing for the discriminator, the distribution over the discriminator. And I mean, so the proof for this is actually well known. There's nothing magical here, but what is nice about this is that given that this now has this particular form, people who work with sampling kind of begin to realize that this looks eerily like something that you know, Langevin dynamics may apply to, right? In fact, if you think about the stochastic Langevin dynamics, stochastic gradient Langevin dynamics, you look at distributions that are written as this nice form. You assume that you have access to the gradients of the potential function h, and what you do is, you know, you define a sequence of iterations that is just similar to the gradient descent with a proper noise injected into the iterations, right? Now, given this understanding, what we will try to do is we will try to sample basically the iterates for the entropic mirror descent, right? As opposed to taking integrals, we're going to be fine with the samples from these the distributions, and that we're going to argue that it's sufficient to run an algorithm to get estimates, right? And of course, the assumption here is that when you go to a sampling problem, you want to be able to give guarantees that you know, in distribution you will converge and so on and so forth. But currently we are a bit far from it, right? So here I'm going to make a big assumption that you can sample from these neural networks, all right? And I mean, people have been doing this, and empirically it's been very successful. And I think this is a compelling research topic. So these are some citations that exactly try to sample from these kind of distributions with neural networks, and they demonstrate that empirically they're very successful, right? And then you basically combine the steps and you're more or less set. You get an implementable algorithm, and what the algorithm tries to do is it tries to solve this mixed Nash equilibrium formulation. As opposed to keeping continuous distributions, it follows these distributions with samples generated from it, right? But as it is, the algorithm is not scalable because as you iterate more and more, there's these samples that just pop out for every iteration, and things become a bit more difficult. Now, then the question is, you know, how do we kind of maintain the same sampling perspective and reduce the complexity and the memory requirements? And what we've done is a basic engineering trick. We replace the distributions at any given iteration by their MMSE estimates, so some mean approximation to the distribution, and then we propagate. In this case, you get constant memory, and the complexity becomes as easy as stochastic gradient descent. Here's the algorithm. I mean, those of you who actually do these kind of things will recognize the terms, but I would be happy to talk offline about the details. So let me provide some numerical evidence. So this is like the mandatory example for neural networks, for generative adversarial networks. For the Gaussian mixtures, this is a 3-layer fully connected neural network. If you apply stochastic gradient descent, you end up getting these kind of patterns. You make things faster with Adam. You get, again, you can kind of figure out the modes, but you will see, as Kostas showed, these modes tend to be super narrow. The estimates of the mixtures become super narrow. And if you apply the mirror GAN or the mirror prox GAN, you get a very nice estimate. The variances are very nicely captured. And it's also interesting to see the evolution of the algorithm here. This is how the stochastic gradient descent evolves. This is how Adam evolves, and here are the mirror and mirror prox GAN. You can also apply this to image generation. So here one example from the Elsan data set with the DC GAN. This is the result for RMS prop. I think the projector is not doing justice, but you tend to see these mode collapses as you iterate more and more. So this is, 4 times 10 to the 4 iterations, then 8 times 10 to the 4 iterations, and then 10 to the 5 iterations. Adam flat out collapses. For our algorithms, we get very good convergence results. We have not managed to make it mode collapse. The algorithm can diverge if you set a step size incorrectly, but it's been working very well. And a concurrent work from this workshop, we tried the extra Adam. The simultaneous update had mode collapse, but now I'm told that I should use some different step size for the algorithm. And there's an alternating version that also works well, that is similar to us. In fact, we looked at some inception scores, and we pretty much have the same inception score with both methods. All right. So the conclusions, the key proposal here was to kind of view the GAN problem a bit differently, try to convexify it, and then try to approximate the convex algorithm in some principled fashion. Now, the big assumption, again, is that the sampling succeeds. Now, I think that, again, this is a great research problem. I think people should worry about this particular research question. Can we actually give some guarantees whether or not we can draw samples from these kind of neural networks? But I think that there's some growing theoretical evidence that Ito diffusions or stochastic Langevin dynamics kind of succeed even though the functions are non-log concave. I mean, we had a spotlight, this SNPs, that shows this can be done, at least for the latent derivative allocation. And the algorithmic insights here is that, you sample for stochastic gradients, and you use stochastic gradients to sample from neural networks and somehow pull them together in this convex optimization framework to make things work. And there's like direct reinforcement learning parallels that we're exploring, which seems to be very successful. And with that, I will end. Thanks for your attention.
Thank you for the talk. Any question?
So I had a question about the experiments. If you go back to the pictures, so you ran that for like, I don't know, like 10 to the 10 iterations?
10 to the 10 iterations.
I don't know, what is that?
10 to the 5.
Oh, I see, sorry, I thought they were not all multiplying. Okay, good. 10 to the 5 iterations?
Yeah.
So so your goal is to keep around 10 to the 5 networks?
No. So in the end, we don't, right? To be able to run this with my finite resources, I introduced this mean approximation with.
Yeah,
Yeah.
could you repeat what you did? So you average them?
So you average the samples after you sample from the stochastic Langevin dynamics and keep one mean estimate for the generator and one mean estimate for the discriminator.
Thanks. Interesting talk. My name's Frans Olihoek. I did a somewhat similar inspired type of approach. I think you might know about it. So in our approach, we really try to characterize, I guess, where the practical algorithm that we came up with converges to.
Mm-hmm.
Do you have an idea whether something similar will be possible here?
You mean in terms of theory characterizing where this algorithm converges?
Exactly.
I mean, if the steps were
it-
exact, you're basically going for this mixed Nash equilibrium point. But of course, you introduce approximations, and then it is. I mean, even some of the gradient estimates are a bit biased, right? So understanding how the bias affects, we've done. But I mean, yeah, it is interesting.
All right. Well,
Ongoing.
perhaps interesting to
Yeah, yeah.
have a chat afterwards.
Sure.
Hi, Volkan.
Hi.
So you said that you don't see mode collapse, but the divergence is related to sampling?
I'd say it's maybe more related to step sizes. So if you think about this, in the outer loop, what we're doing is basically just doing mirror prox or entropic mirror descent. And you have to set step sizes for these algorithms.
Right. So
Right.
even if you don't get good samples, you expect that you are going to converge, or?
No. I'm assuming if the sampling succeeds, then things work, right? I'm not making any vacuous claim here.
Okay.
And I'd like to thank my PhD students Yaping Si and Chen Liu. I mean, this was a major thing to produce, just given our resources. So, any other questions?
Okay, I have just one last question. So you mentioned that like the mixed equilibrium always exists, but what are the conditions on the existence of the mixed equilibrium? Like you have the like there is condition on the function.
I mean, just the way I wrote with the bilinear games, this is well studied in Glicksberg. I would just take a look at the exact conditions.
So if the function is like smooth enough, it's okay, I guess.
Function is in the linear mapping, you mean?
I mean, like when you look at the WGAN, the properties of the function are good enough for the mixed Nash equilibrium to exist.
No. So whatever you put neural networks don't matter.
Okay. Okay, so let's.
I have a related question then, like, is it for also any distribution, like class of distribution you're considering, or is it have to be like an infinite family?
When you go for a distribution over the GAN parameters, is inherently infinite dimensional because you think of a fixed parameter set in d dimensions, and now you define a distribution over all possible parameters in that space.
Yeah, but then the class of distribution, like you're considering?
Is all
Okay.
distributions in that space.
Okay, let's thank the speaker again. So now it's going to be the last contributing talk of this morning, and it's going to be given by Pierre Giuseppe Sessa, and it's going to be about price of anarchy.
Hello, everybody. I'm going to present our work on binding the inefficiency of continuous action games using submodularity and curvature. And this is joint work with Professor Marian Kangarpour and Professor Andreas Krause at ETH. So game theory is a powerful tool for modeling many multi-agent decision-making problems, but also can be used to design distributed optimization algorithms. So as two motivating examples, consider the following budget allocation and sensor coverage problems. In a budget allocation problem, we have a market composed by customers and media channels, and there are a set of advertisers which would like to invest in each media channel to maximize the number of activated customers, meaning customers that buy their products. This problem can be formulated as a game and analyzed using game theoretical tools. On the other hand, suppose there is a central authority which would like to allocate sensors to location in order to maximize, for instance, the probability of detecting an event. It turns out that for this problem, a game can be designed to actually lead into a distributed optimization algorithm. Our focus in this work was on continuous action games, so games where the strategies for each player are uncountably infinite. They arise in many machine learning applications where finite action can be limiting. As an example, consider the case where advertisers want to invest continuous amount of money in each media channel, or to the case where we not only want to allocate sensors to locations, but we want to decide some continuous amount of energy or time spent by the sensors in the locations. So more formally, we consider games with continuous actions G that are defined by the following tuple of 4 elements. So number of players n, and then for each player strategy set, which we assume lives in a non-negative orthant, and a payoff function which the player wants to maximize. We can think of, in the budget allocation game, for instance, the payoff function for advertiser I is the number of customers activated by himself, and a social function gamma, which is the function that the game planner would like to maximize. So the game planner, we can think of him in a budget allocation game to be the market analyst, which could care about maximizing the number of activated customers regardless by which advertisers. So you see that already here there are different interests. So the interest of the game planner, which is of maximizing the social function gamma, which is not aligned with the interest of the players, which is of maximizing the individual payoffs pi I. And this is why sometimes games are inefficient. And a central question is to quantify or somehow bound such inefficiency. And in this work, we are going to provide efficiency bound, inefficiency bound for a class of continuous action games of this form. And more specifically, we are going to extend existing and lift existing results from finite action games to continuous domains. Now, before defining what I actually mean by this inefficiency, let me just define what a coarse-correlated equilibrium is in such games. It is a probability distribution sigma over the joint action space, such that for no player there is any incentive in deviating from the outcome sample from that distribution, which means that in expectation the payoff of player I under that distribution is greater than when player I deviates and chooses a strategy as I prime. And now CCEs are the largest class of equilibria. They contain pure Nash and mixed Nash. And more importantly, no-regret learning algorithms converge to CCEs of the game. So it may be sound unreasonable to assume that the players are playing Nash equilibria because they may be hard to compute or may not even exist. It is much more reasonable to assume that the outcome of the game actually converges to one of such equilibria. So with this in hand, we can define what we mean by inefficiency by the well-known price of anarchy, being of any coarse-correlated equilibrium, being the ratio between the social optimum, so what is the goal of the game planner, with the worst possible expected outcome following by any of such equilibria. And now this set delta is the set of all the possible CCs of the game. Now, price of anarchy has been bounded for a large set of games, and a class of game with bounded price of anarchy are the well-known value utility games defined by Veta in 2002. They are games with finally many actions, though. So as our main contribution, we are going to extend the class of value utility games defined by Veta to continuous domains. I also am going to show you that the budget allocation problem and the sensor coverage problem falls in this class, and I will provide you also some numerical examples. So in value utility games, they are defined over a ground set V, like set of locations, for instance, where we want to, let's say, allocate sensors. And the social function for this game is a set function. So it's a function which takes value for all the possible subset of set of locations. Now, the price of anarchy was bounded for this class of games by exploiting a property of set function, so-called sum-modularity property. For set functions, sum-modularity property is equivalent of asking that the function satisfies diminishing return. And what does it mean is that for all the possible couple of sets, A included in B, and for all the elements that we can add to these sets, we have an higher increment if we add the element to A than if we add the element to the set B. And to illustrate this, let's say this function here now represents the area covered by the sensor, which we like to maximize, for instance. If we have a sensor in location A and we add a sensor in location L, the increment here is just this red area. Well, if we have two sensors in locations B and we have the same sensor in location L, now the increment has decreased, and it's this green area here. Now the question is, can we say something in case the function, it is actually defined on continuous domain? So in our setup, so recall the function, the social function is a function defined over dot negative orthant. So can we somehow say something if we not only want to allocate sensors, but we also want to decide some continuous, let's say, amount of energy spent by the sensors in the locations? And the answer in this case is yes. And in fact, in 2017, Bian defined the class of DR sum-modular functions, which are functions which are defined over continuous domains and satisfy a diminishing return property really similar to the sum-modularity for set functions. In fact, if the domain is binary, it coincides exactly with some modularity I showed you before. But in general, now without going into detailed definition, for if the function is twice differentiable, it is DR sum-modular if and only if its Hessian is element-wise non-positive. It means that the class of DR sum-modular functions can be convex, concave, but also none of the two. And that is why this property has been used to derive approximation, for instance, algorithms for the maximization of this function. Now, with this, we can define the class of value utility games with continuous strategies, games which satisfy the following three conditions. Now, in condition one, we ask that the social function is a monotone DR sum-modular function. And condition 2 and 3 are the same condition like defined by Veta in 2002, but just adapted to our continuous action space. And a similar definition was also provided by Mahara in 2015 when they considered integer domains. Now, our main result, similarly to previous work, is that the price hierarchy of such game is upper bounded by 2. And also similarly to previous work, we can further refine this bound. And to do so, in this work, we define what is the notion of curvature of a monotone DR-sum modular function. So we define the curvature of a monotone DR-sum modular function with respect to a set Z, which is a subset of the domain, the following number alpha of Z, which lives in 0, 1, and somehow measure how the function is far from being an affine function. In fact, if alpha of Z is 0, if and only if the function is affine in Z, otherwise it's just 1 minus the infimum of this ratio of gradients. Also, a more general definition can be provided for non-differentiable functions. Now, using this definition, we can refine this theorem by affirming the following. So if we define the set S tilde to be the biggest hypercube, which contains all the sum of possible strategies, then the price hierarchy of such games, it is indeed upper bounded by 1 plus alpha, where alpha is an upper bound for the curvature of the function, of the social function, with respect to this set S tilde. Also, interestingly, and also differently from previous work, we can extend this theorem to a class of non-sum modular functions, which, however, satisfy approximate sum modularity properties. Now I'm going to apply these results to our budget allocation game, where recall we had a market composed by media channels and customers, and the advertisers, which in this case are N, want to invest amount of money in media channels to actually maximize the number of customers which are activated. And there are some activation probabilities with which advertiser I activates customer T via channel R, while the market analyst wants to maximize the number of customers which are activated regardless by which advertiser. Now, this problem can be formulated as a game, and we can show that it actually satisfies the three conditions I showed you before. Therefore, we can plot the obtained price hierarchy bound as a function, in this case, of somehow the connectivity of the market and of the maximum activation probability. And we can show that our bound actually depends on the curvature of the social function, which in turn depends on these two parameters, and can strictly improve the bound of 2, which was provided by Maharia for the integer case. I will now switch gears and show how this game can also be designed to distributively optimize, maximize monotone DR-sum modular functions. So let's say now we have the following problem of maximizing a monotone DR-sum modular function subject to this joint constraint set. I will show you that the sensor coverage problem can be also formulated in this manner, where each constraint set is just like budget constraints, for instance, for each sensor. Now, in order to actually tackle this problem, we can borrow the well-known idea by Martin et al. 2013, which is the one of setting up a game to actually maximize this function. And in this game, we have n number of players, where each player has strategy space equal to the set xi, and the payoff for each player is exactly this difference, which, if you recall, is exactly like condition 2 of the valid utility games satisfied with equality. We can then show that this game is a valid utility game with continuous strategies, and as a corollary of our price hierarchy bound, we can affirm the following. So assume that there exists a no-regret learning algorithm for each player of this game, and let's call d no-regret the simultaneous implementation of such algorithms. Then d no-regret converges to a distribution with approximation guarantee 1 over 1 plus alpha. And why is that? Simply because 1 plus alpha is the price hierarchy of such game, and therefore, like a no-regret algorithm converges to a course-correlated equilibrium, and we know how such equilibria are far from the social optimum. And this guarantee, depending on alpha, can improve on the existing guarantee like provided by Bian. Now, I will apply this to our sensor coverage problem, where we want to allocate sensors to location to maximize the probability of detecting an event. A game can be set up as outlined before, and it turns out that for this problem, online gradient descent is a no-regret algorithm for each player, because the function gamma is also player-wise concave. And therefore, we can compare the performance of d no-regret with the Frank-Wolf variant provided by Bian, and we observe that our distributed no-regret algorithm converges faster than the Frank-Wolf variant. However, for 3,000 iterations, the two algorithms perform equally. To conclude, we bounded the inefficiency of a class of continuous action games using DR-sum modularity and curvature. And we show how these bounds can be used to tighten existing results on DR-sum modular maximization. And we also believe that the introduced notion of curvature can be used to tighten existing guarantees. With this, I thank you for your attention, and please come by to our poster if you want more details. Thanks.
So there is questions.
Thank you for the talk. About the distributed algorithm, we actually have a paper in ICML that solves even, you don't have to you get 1/2 approximation, we get exactly 1 minus 1 over E approximation. We also define the curvature. There is, instead of, 1 over 1 plus alpha, you get 1 minus, the stronger curvature.
So I'm not sure I'm familiar with this paper, and is it was considering the continuous setting?
Yes, so the paper is submodular optimization, discrete and continuous settings. That's the title.
Okay. I'm sorry, I'm not familiar with this paper. I probably will go through it, but it was, so
we don't consider the games, right? So we just go to decentralized submodular. Right, so I'm only talking about the distributed setting, not the game.
Sure, and it was which algorithm? So how the algorithm was actually? So which kind of algorithm was implemented there?
So it is basically we came up with stochastic Frank-Wolf.
And the guarantee was 1
minus 1 over E, if general, and then you get, if you have curvature, you get much better.
But was it assuming coordinate, like player-wise concavity? Because our guarantee actually here assumes that there is a no-regret algorithm, and to actually have no regret algorithm, in this example at least, we needed player-wise concavity of the function.
We are assuming there are some modularity, if that is your question.
Okay. No, I'd like to mention that this actually the guarantee that we obtain. So our guarantee strongly relies on the existence of a no-regret algorithm, which in our case, to actually implement this no-regret all-line gradient descent distributed fashion, we needed also coordinate-wise concavity. So I'm curious to understand, to know actually how you could get the same guarantee without concavity. Yeah.
Any other question? Okay, so let's thank the speaker again. So this is the end of the morning session, and so the afternoon session starts at 2.